One of the biggest mysteries in all of science is this. Why is our universe flying apart faster and faster every single day? The official story, the one you hear most often, blames this mysterious force called dark energy. But what if that story is just wrong? What if the force pushing everything apart isn't some new, exotic energy, but gravity itself, just working in a way we never, ever expected? Okay, let's dive right into this cosmic detective story. So, here's the central mystery. For the longest time, we all figured that the expansion of the universe, the leftover momentum from the Big Bang, had to be slowing down. I mean, gravity pulls things together, right? It should be acting like a brake. But then in the late 1990s, astronomers looked at these distant exploding stars and saw the complete opposite. The expansion is speeding up. Something out there is hitting the cosmic gas pedal hard. Now, to really understand the alternative theory we're going to explore, we first have to get to know the prime suspect in our investigation, the idea that currently dominates all of cosmology.
The standard model of cosmology, it's called Lambda CDM, or Lambda CDM for short, has what seems like a simple explanation. It says the universe is filled with this thing called dark energy. It's this weird anti-gravitational force that's apparently woven into the very fabric of space-time, and it makes up a whopping 70% of everything in the universe. The only problem? We have absolutely no idea what it is.
Now, the simplest way to kind of shoehorn this dark energy into the math is with something called the cosmological constant. It's represented by that Greek letter lambda. Einstein actually played around with this idea a century ago. It's basically a fixed amount of energy that's just inherent to empty space itself. And this background energy has this bizarre repulsive effect that pushes the universe apart. Okay, get ready for this, because this is where the whole dark energy story starts to look really shaky. When our best theories from quantum physics try to calculate how much of this vacuum energy there should be, they spit out a number that is 120 orders of magnitude bigger than what we actually see. That's a 1 with 120 zeros after it. This isn't just a small rounding error. It's been called the single biggest failure of a prediction in the entire history of physics. It casts this enormous shadow of doubt over the whole idea. So, a problem that big has led some scientists to think, hang on a minute, what if we're barking up the wrong tree entirely? Instead of inventing a brand new, mysterious energy to make the math work, what if our theory of gravity itself is just incomplete? And this idea isn't even brand new. Almost 40 years ago, long before we even knew the universe's expansion was accelerating, an amateur physicist named Marco Saba had this amazing gut feeling. He just speculated that on the very largest cosmic scales, gravity might flip and become repulsive, causing whole galaxies to push each other away like super-gravitons. It was an incredible piece of intuition that's now getting a serious second look. So let's just boil this down, because this is the absolute key difference. The standard model adds a new ingredient to the universe, this dark energy stuff. The alternative, which goes by names like F of our gravity, it changes the recipe. It actually modifies Einstein's law of gravity. It suggests that this acceleration isn't caused by a weird energy, but that it's just a natural consequence of how space-time's geometry works on huge scales. Okay, so how do you actually do that? How do you take an idea like gravity is different and turn it into a real, testable, scientific model? How do you go about rewriting the rules of gravity? Well, what's so amazing is how simple and elegant it can be. One of the leading models, it's called the Starobinsky model, just adds one single extra term to Einstein's famous equations of general relativity. Just that alpha r squared bit, that's it. One small mathematical change, and it fundamentally alters how gravity behaves on a cosmic scale. And this is where it gets really, really compelling. It's like a cosmic two-for-one deal. This single, simple modification could potentially solve two of the biggest puzzles in cosmology with one elegant mechanism. It could explain the super-fast inflation of the universe right after the Big Bang and the gentle acceleration we see today. For the standard model, you need two totally separate, unrelated explanations for those two things. So how does it actually work? Well, on these gigantic, almost empty scales between galaxies, that new little term in the equation starts to dominate, and its effect is to create what's essentially a negative pressure. In cosmology, negative pressure causes repulsion. It's not some magic energy, it's an emergent property of space-time itself, basically making Marco Saba's super-graviton idea a reality. Okay, a beautiful theory is one thing, but does it actually match what we see out there in the real universe?
To find out, scientists have put this new suspect on trial, confronting it with the very best evidence we can gather. The key witnesses in this trial are things like type A supernovae. These are exploding stars that act like standard candles because we know how bright they're supposed to be, so we can measure their distance. And we also have baryon acoustic oscillations, which are these leftover sound waves from the early universe that serve as giant standard rulers. Together, these things let us map out the entire expansion history of the cosmos.
And here is where our cosmic detective story takes a huge plot twist. When you run the numbers and check the predictions, this modified gravity model is an almost perfect mimic of the standard dark energy model. The predictions are so close, we're talking within about 1%, that if you just look at how fast the universe is expanding, you literally can't tell them apart.
To get really precise about it, scientists look for this tiny statistical deviation. And the latest data, well, it kind of hints at a deviation, but only at a low confidence level, what's called 1 sigma. Think of it as merely suggestive evidence. But when you look at the more scientifically robust 2 sigma level, which is much closer to being conclusive, the models look completely identical. The clue is tantalizing, but it is not a smoking gun. So, after all this, after interrogating all the evidence, where does that leave our investigation? Well, it leaves us in a fascinating, and maybe a little frustrating, stalemate. When we bust out the advanced statistical tools to really compare the models head-to-head, we get a split decision. One tool, which just looks at which model fits the data best, actually gives a slight edge to modified gravity. But another tool, which penalizes theories for adding extra complexity, gives a slight edge to the simpler dark energy model. It's a total statistical dead heat. The data we have right now just isn't good enough to declare a clear winner.
But wait a minute. You might be asking, if gravity is modified, why don't we see anything weird happening here, in our own solar system? Well, the theory has a really clever alibi for this, and it's called the chameleon mechanism. The idea is that this extra gravitational effect is sensitive to density. Out in the super low-density vacuum of deep space, it's switched on. But in crowded, high-density places like our solar system, the effect gets screened or hidden, and good old Einstein's general relativity works perfectly, just as we've always measured. So what's the tiebreaker going to be? Our best hope, it turns out, isn't just in looking at how fast the universe expands, but how things grow within it, how galaxies and giant clusters of galaxies form over billions of years. Modified gravity predicts subtle differences in this growth rate compared to the standard model. Upcoming telescopes might finally be able to measure that, and that could finally be the clue that cracks this case wide open.
And that leaves us right here, staring at one of the most profound questions in all of physics. Is 70% of our universe made of some completely unknown substance that's actively pushing it apart? Or have we just been using the wrong rulebook for gravity this whole time? For now, the case remains open.